Yeah, good morning. I think in the last session we discussed about the streaming stored video. In fact, it's the one on very important topic because the current day we have the lot of videos that are being used in many of the applications, maybe in sort of practical scenario, and hence I believe stream stored video understanding is very important, and even I expect some students to do some research work on this. Of course, continuing our discussion with the multimedia networking, it's very essential to understand how the voice communication is also done. There are a lot of voice communications applications have been developed. And because of that reason, even during the pandemic period, we could able to make a lot of communication in an effective way. Of course, there are applications that are giving the voice communication over the internet protocol, and hence it is called voice over internet protocol, which is represented as VoIP. This is the one on very oftenly used by the people for their voice communication. The very advantage of this communication is it will be using the circuit switched link connectivity. It means that whatever we have the telephone connection, through that only we can make the communication. That's why it is very popular. And since it will use the internet for the communication, so the possible cost is very low for this communication. However, we can have the voice communication in an effective way along with the presentations. With this, the introduction, let us start this voice over internet protocol. I think this is the one where the voice has to be transmitted over the internet, and we need our technology to support for this. You know how exactly the voice is communicated. Voice is also called as real-time communication. I am speaking to you and you are able to listen me. Okay, so it is a continuous communication that is going from my side and it is being received by the people on the other side. So here there are some basic characteristics of voice. I think probably in the future slides I will be discussing in detail of that. But before that, let us understand how the technology works in voice over internet protocol. Basically, the voice over internet protocol will be adopting the internet for communication, and also the circuit switched network is adopted, so that there will be a very effective communication over the network, and hence it will be using a few of the technologies called the best effort technology. What do you mean by best effort then? I think in the previous session also I mentioned about the best effort communication. The best effort communication or technology says that especially we use this best effort in case of the UDP protocol. I think you all know that UDP is very popular for the real-time communication, that is audio or video communication. So this user datagram protocol adopts best effort technique. It means that whatever the packets received from the server or from the client, that will be forwarded to the other side to reach the destination at the earliest. Okay, so the packets will pass through different path depending on the network congestion or the traffic, and hence it will always try to reach the destination at the earliest. So there are possibility of loss of packet This was because of loss of packet. We can expect that there is a loss in data, and hence there are some applications which are very sensitive about the delay. For example, due to loss of packet, what is the possibility? We have to make the retransmission. If the retransmission is accepted, then there will be a lot of delay occurs in the transmission of total uh, packets. During that time, the delay incurred in the completion of transmission is high. But I am speaking to you. If you do not receive my word immediately and the next word reaches to you before the previous word, probably it is a meaningless one. So during that time, we are going to say that the packet is died, okay, or otherwise we say it is the lost packet, which even if it is retransmitted, it is of no use for the applications. And hence there are applications where they are very sensitive about the delay. In such application, the best effort technique has got a limitation. However, this can be overcome by the TCP. But again, there also, as I told, the reliability is good, but however, the delay makes sense. So now we will go with the why the packet loss happens in the network. To understand the loss of packet, usually what happens whenever there is a communication from one peer to the another peer through the network, there will be a lot of network come in between. When we find different networks communicating each other, there might be a chance that one of the network will be having a lesser capacity, and hence the weak network will forward the packets very slow. Okay, the delay incurred in those network will be very high. If the delay is too high, and if the expected doesn't reach then we say that the loss of the packet will be lost, and hence it will lead to the problem. That's the reason the packet loss happens. And this can be overcome by means of two techniques. One is UDP, other one is TCP. As I mentioned in the previous explanation, UDP as an user datagram protocol, it will be adopting the best effort technique and try to reach the destination at the earliest, so that it is the most suitable for the voice communication. Because I am speaking to you, and if a word or a one letter is missing in my speech to reach you as a packet loss, it will not make much difference to you. You can understand what my intention or what is the meaning that I'm speaking to you. But the other way, if it is not reached to you in time, and if it is reached to you after the next sentence, probably it is of no use. That's why the UDP stands better than TCP. Whereas in TCP, what happens? Every such failure in the transmission has to be retransmitted, and hence it will take its own time for the retransmission. That will lead to so many other complications, like increasing in congestion. Increase of congestion will have a cumulative action, saying that the further packet losses will happen, and finally it may reach a stage where the uncontrolled congestion in the network. So that's why UDP makes an upper hand over the TCP in voice communication. And as I mentioned you earlier, Skype is the one which is the most popular application that is being used by the people all the time. And this is the one application which is adopting the voice over internet protocol. And of course, there are techniques to overcome the loss of packet or the error in the packet. So that is done by the technique called forward error correction. This forward error correction is one of the most popular techniques of overcoming the errors that are happened in the network communication. So here you can reduce the retransmission, and whatever the packets we transmitted, they will carry some redundancy, and hence it will correct at the receiving point only. Any error has occurred, it will be corrected automatically at the receiving point. Anyway, these are some of the issues that have come across in the packet transmission. Before going to the further discussion, let us understand the voice over internet protocol and its end-to-end delay requirement. The total delay that occurs in the transmission will always be having different components in it. The delay, what happens in the communication, will have different component, 4 different components. You can see here. One, the first delay is called transmission delay. The second one is processing delay. Third one is queuing delay, and the fourth one is the propagation delay. Here, the queuing delay is the one which will always create some chaos in the network. It all happens because of the busyness of the routers in the network. And because of that reason, we may feel jitter in the network. Jitter means varied delay from one packet to the another packet while reaching the destination. When the delays are very high, that is, it is at the noticeable level, then it will create a lot of problem in the voice communication, and we say it will impair the interactivity. Okay, so when there is an interaction is going on, then the larger delays cannot be accepted. Rather, we have to reduce the delay as can as possible and to make the conversation smoother. You must be knowing that when we are talking to the very long distance people, probably I am talking to a person from India to US. After speaking, I need to give some delay to listen to the other person. If I am trying to speak one after the other, probably the other person is unable to speak from the other side. The delay, the propagation delay will be more when the distance is more between the two persons who are in the communication. So if the delay is too much, then it leads to inconvenience in our interaction. So that's why the basic aim of any such voice communication is to reduce the delay as can as possible. And what is good for the interaction? It is expected that the packet transmission delay should be less than 150 millisecond, which includes all these delays what we mentioned on the above. Okay, transmission delay, processing delay, queuing delay, and the propagation delay. And somewhere which is slightly more than 150 millisecond is acceptable. But if it is crashing 400 millisecond, it is the worst condition for the application to run. That's the reason usually we'll always try to reduce the delay to a great extent by reducing the possible queuing in the transmission. Now we'll discuss on the session initialization. I think how exactly the session will initialize by making the connectivity with the destination through the IP address, and also the port address is used for that purpose. And at the application layer, we do the encoding of the what the voice message we have been transmitted. So all these are the part of voice over internet protocol. There are some value added services in VoIP. They're called call forwarding, screening, and recording also, which is really very exciting applications that can be done, because nowadays, because of these techniques, we could able to talk 2 or 3 people simultaneously over the teleconference, and I think even call forwarding is possible. I am not at home in the office, and my call to the office may be forwarded to my mobile. Okay, so like that, even screening is possible. I can screen out the calls, and I can block the calls. I can allow the call depending on the need. Okay, even now there are applications that are really working on the recording of the communication, because sometimes it may be very important for us to record the conversation and to put forward for the needful. Anyway, all these are the part of our VoIP. Now let us look into the basic characteristics of the voice communication. The very idea or characteristic in voice communication is what we talk is not a continuous process. You see, I am talking to you. There is an in-between silence after probably spell out a few phrases, few words. I will pause a while and again I will continue. Okay, so this silence is of an unwanted thing, or it is not necessary to make a transmission. Whereas what is that I am communicating or speaking, that is supposed to be communicated onto the other side. The silence can be created on the other side without the transmission. So this is the major technique in making the voice communication more and more effective. It means that if I am speaking now, if I speak about 1 minute to you, probably the talk spurt means my words pronunciation comes only about 60%, almost about 30 to 40% of my speech I will make silence. I will keep silence. Okay, so this silence can be avoided in transmission. Only 60% can be transmitted. Okay, by this what happens? The transmission speed will increase. The transmission speed will increase greatly, and also that will make an efficient bandwidth utilization, and also the technical challenges can be overcome easily. So now our application has to take care of these aspects, like identifying the talk spurt and allowing the talk spurt through the bandwidth, and trying to avoid the possible silence. Even if the silence is sent, it will be having a very less bandwidth, which will move faster in the network. Right, then application header adds these chunk, because whatever we speak, it will be forwarded as a chunk. It means number of packets are grouped together and then it is forwarded. So those chunks are added with some headers, and they will be forwarded to the other side. Both the chunk of data and the header together, it is encapsulated either with the UDP or TCP segment. You know, the transport layer will use UDP or TCP, whichever you choose, accordingly it will act. Application sends segment into socket on every 20 millisecond during the talk spurt. This is an average calculation what they have made. Let us understand a little more onto the packet loss and delay. The network loss is an IP datagram loss due to the network congestion. As I was told you earlier, the reason might be due to the queuing problem. Queuing happens in the router. When more number of packets arrive to the router, these packets will be kept in queue in the buffer, and sometimes the buffer may be overflown. When the buffer is overflown, some of the packet will be lost. This might be the one reason. The delay loss is also possible. An IP datagram arrives too late for the playout at the receiver side. I have spoken a word which has reached after the statement is completed. It means that word will not be having any sense to play. That time that a too late packet or a word will be lost or it will be destroyed. These are some of the issues. So the loss occurs due to the greater delay than the expected one. These delays, as I told you, because of processing, queuing, and end system delays are also incurred. Which is if the delay is more than 400 millisecond, I think it is intolerable. Usually the loss tolerance is acceptable at in the voice communication. The packet loss rate from 1% to the 10% is said to be unacceptable because as I told you, in any speech, if we miss one word or one statement, or sorry, one letter, it won't make much difference in the meaning of the communication. That's the reason loss is acceptable, but it should be within 1 to 10%. Now let us understand how exactly the delay will make some problem in the voice communication. Even in video also we have showed this kind of diagram wherein we say that how the communication takes from one point to the another point in the network, and when it is received, whether it is really useful for the receiver and to play it back. Here you can see that the transmission happens at a constant rate. Okay, it is going in a constant rate. It is being transmitted. This is the scenario that happens in the network. Okay, you see that though the transmission has an uniform delay, this is the delay. Okay, in every step it has got. So let us assume that each one is a chunk. Okay, different chunks are transmitted. Okay, chunk number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Let us assume there are 11 chunks are there, and they are transmitted with an equal delay here. But you see in the network what is happening. So network cannot take the equal time to transmit or to reach the destination. So you can see the first chunk has taken this much of delay. The second chunk has taken a very small delay. Third chunk, small delay. Fourth chunk, small delay. Again, for the fifth chunk, it has taken too much delay. It is again increased, reduced, increased too much, reduced, reduced, and then reduced. Okay, so this is called variation in delay of each chunk transmission. This variation in delay is nothing but jitter. I say variation in delay in chunk transmission is nothing but jitter in the network. If the variation delay is constant, then there won't be any jitter. Okay, so there will not be any jitter in that case. So jitter happens only when the variation in the delay. Here jitter is 0. In this case, jitter is 0. But here much jitter you can identify here. So this jitter really makes some problem in the network because all the chunks will not reach the destination in time. Okay, one is reached early, other one is reached in time, the third one is reached much delay. Okay, since it is a real-time communication, too much of delay cannot be accepted, or otherwise that leads to the loss of either a chunk or a packet. Why? Because the playback at the receiving point requires a constant delay between each of these chunks. Okay, so you can see here what happens at this point. Okay, as I was told you in the previous communication also, that every such transmission will be buffered at the client point. Okay, So the data is buffered, but because at this point the second chunk is being played, okay, and there is a big delay, you can say. So now third is played, no problem, it is already reached. Third is first is reached, second is reached, third is reached, fourth is reached, fifth, sixth, seventh, eighth. Okay, but here you can see that at this point, this is supposed to play this particular the chunk, but however that is not reached because of this larger delay. In such situation, there will be a problem in playback. So what is that expected is either the jitter should be as minimum as possible, or otherwise the buffer size has to be increased depending on the jitter. If the jitter is more, buffer requirement is more. If the jitter is less in the network, obviously buffer requirement at the receiving point is lesser. The standard what we expect in the network is any chunk of data transmission should be less than 20 millisecond. Sorry. Uh, Let us discuss a few techniques that will overcome this problem. Two techniques are used for playout delay. One we call it as a fixed playout delay. Another one is an adaptive playout delay. Now the fixed playout delay, wherein you will be having a chunk exactly of q milliseconds time it has taken and it was generated, and it has got a timestamp of t, that is play out chunk at the rate of t plus q. The reason is the chunk play out time is q and the delay is timestamp is t. So it will require t plus q time to play out. If the chunk arrives after t plus q, it means the data arrives too late and hence the data is not of useful. It is to be destroyed or it is lost. Okay, so that is why we have to do some work on this. But here the question is, what should be the delay of our playout? Okay, if you fix the delay of q, what is that we have fixed here is q millisecond is the delay fixed for every chunk. After every chunk received, it will wait for q milliseconds. Okay, q millisecond in the buffer, and then it is played back. But even then, if it the packet is or chunk is received late, then it is not possible to play it. So that is why now the question arises. If it is delaying too much, we may have to increase the q value. Okay, it may become q plus 2. Okay, or otherwise let me call it as q dash. So q dash is greater than q. Okay, you have to increase the play out delay so that you are giving more time for reaching the chunk to your point. Okay, but that is again a problem in the real world, because you know, whenever we are making transmitting the real time applications or data, it should be reached the destination with a shortest delay. Otherwise there will be a lot of inconvenience in such communication, especially when it comes to an interaction. Okay, when I speak, I am expecting an immediate response from the other side. If there is a much delay, I may be trying to speak the other words thinking that the other person has not spoken to me. So what happens the moment I start the next word, his word has come, and hence there will be a collision of such discussions. So that is why a smaller delay is always expected. So that is why a trade-off is required in choosing the queue. Large queue will lead to less packet loss, no doubt, because packet loss happens only when the packet is reached after the delay queue. Okay, So if queue itself is more, then there won't be loss. Losses are less, but that is not acceptable. When a smaller queue we use, it is better for interactive experience, but only thing is the jitter should be as minimum as possible in the network. This scenario is being explained in this system. You can see that the voice over internet protocol fixed playout delay is explained in this system, wherein the sender generates packets every 20 millisecond during the talk spurt. You can see this. Every 20 millisecond, the sender is generating the packets. Okay. The first packet is received at a time R. You can see this. The first packet is received at the receiving point at a time R. Okay. The first playout schedule begins at P. We say it will play out begins at this point. Okay. So now what is this delay? R plus P is the starting time. So that delay is P. So the playout delay is P. Okay. And what we expect for the second one is obviously the second playout is R plus P plus P, like the 2P we can say otherwise. Okay. Likewise, the delay will vary. You can see that it will be delayed like this. Here, actually, it is not getting the expected packet, and hence there is a loss of packet. If this is lost, this cannot be played back because the packet has not yet reached. It will be reached at this point, which is delayed by some amount. Okay, this is because of this larger delay in the network. Okay, and hence we say that this packet is lost. What is the solution for this? Increase this P. Okay, let us say P dash, which is more than P. Okay, R plus P is the playout period. R plus P dash, not the P dash now. Okay, so if it is started here, all the packets are reached in time and they can be played smoothly on the other side. So we say playout schedule is P dash minus R. Okay, so this is exactly the way the VoIP works with the fixed playout delay. But with the fixed playout delay, there is an issue, as we mentioned. The trade-off in identifying the playout delay is the major problem. Okay, because it all depends on the network. Sometimes the jitter may be too high, sometimes it may be less, and hence deciding the playout delay makes a major issue in the fixed playout delay. So that's the reason there is an alternate for this, and that is called adaptive playout delay. This adaptive playout delay, excuse me. This adaptive playout delay has a goal of low playout. It means that uncertain issues will be there in the network, and because of that reason, the playout delay cannot be fixed properly. So, but whereas whatever you fix, it should be as minimum as possible and low loss rate also. The packet loss should be as minimum as possible. This is the goal. Then how to approach this? For this, there is a technique in case of adaptive playout delay adjustment. Basically, it will estimate the network delay. Estimation means it is the pre-work that is done in the network, and it will adjust the playout delay at the beginning of each talk spurt. Okay, before starting such communication, it will analyze the possible delay in the network, and it will calculate. Typically, it will calculate the possible delay, and it will fix the playout delay appropriately, and which is adjustable also. Silent periods are compressed and elongated. See, that is the advantage is taken. Chunks still played out at every 20 millisecond during the talk spurt. Obviously, the delay at the transmission side remains to be the constant. Adaptively estimated packet delay. I think how exactly we do estimate the packet delay. So that can be done with the help of this equation. I think the same kind of equation is required when we are calculating the TCP round trip time. Okay, round trip time estimation will also go with the similar kind of equation. Here, the estimated delay for the ith packet estimated delay is calculated as 1 minus alpha. Alpha is a constant, a small constant, and that is multiplied by d of I minus 1. It means that this is the delay of previous packet or chunk. Previous one. Okay, we are considering the previous packet experience in the network, and hence we are able to estimate the current packet. So that is the idea in this. Then that is added with alpha, again the same constant, multiplied by Ri minus Ti. What is Ri? The time at which it is received. The chunk is received at the receiving point. What is Ti? It is the time that is sent. At what time it has been sent. It is called timestamp also. Okay, so Ri minus Ti is the actual, and it is the basis for this calculation. But however, we would like to relate this with the previous packet, because previous packet transmission gives an idea how at what speed the network is being transmitted the packets. So taking that, because it is multiplied by 1 minus alpha. This constant help us to regulate the di minus 1 value. Okay, so by varying this constant, you can vary this component, this entire component. Okay, so it is helpful for us to estimate or predict the possible delay in the next packet or the chunk. Here the next packet is ith packet. Hope you understood this equation perfectly. Now also it is useful to estimate the average deviation of the delay Vi. Any such transmission delay, it will be varying. Since it is varying, the jitter happens. The variation of delay is nothing but jitter. Okay, this is called jitter. If this is the jitter, then what is our requirement is how widely it is varied. Okay, it means that what is the minimum variation to the maximum variation. That is very, very important. Okay, this is called deviation. If the deviation is small, then it is really good. If it is large, if the deviation is large, it is not good in the network, because if the deviation is large, jitter is more, and prediction of the arrival of the packet is very, very difficult. Okay, and hence variation gives us the variation of delay gives the idea about the deviation of the delay. Here deviation is again calculated with the support of previous packet calculation, Vi minus 1 multiplied by again a constant, and then this is added with Ri minus Ti minus Di. I think these two components were taken earlier. This has been subtracted by the previous delay incurred. So it means that all these three components are helpful in finding out the deviation, current deviation. So estimation of DIVI calculated for every received packet, but used only at the start of the talk spurt. So before starting the talk spurt, only you can adopt the deviation and the delay. So the prediction will always help us to make the smooth play out at the receiving point. And also we say that this will help in reducing the possible delay in the transmission also. Now you can answer this question that how does receiver determine whether the packet is first in a talk spurt or not? This is one important need for that. Okay, whether it is the first talk spurt or the middle talk spurt. That's the question. So very simple. If a difference of successive stamp is greater than 20 millisecond, then the talk spurt is just begin. Okay, it is the first one. With loss possible, receiver must look at both the time stamp and the sequence number. So if the difference of successive stamp is more than 20 seconds and the sequence number is without gap, then we say it is the successive talk spurt, and hence we will identify it. Okay, these are some keys for identifying it. Till now we discussed about the loss and the delay and all aspects, but all these are connected with the basic challenge that the why this loss happens, or otherwise if the loss happens, how it can be overcome. There are few challenges in it. The challenge here is to recover the packet from loss. A small tolerable delay between original transmission and playout is acceptable. Here, each transmission of acknowledgement whenever a loss occurs, it will take too much of time. That is called round trip time. Okay. When a packet is transmitted and it is lost or corrupted, okay, then a acknowledgement comes saying that negative acknowledgement may come. Okay, then it has to retransmit it again. Okay, this will take a round trip time, additional round trip time. But it is too late to receive on the other side, and in case of audio and playout is not possible. Again, it will be lost. Okay, so the very solution for this is using the forward error correction technique. So whatever the packet has been transmitted from source to destination, if it is corrupted with an error, this error is corrected there only, corrected at the receiving point without asking for the retransmission. Okay, so it will be corrected and it will be used here. What is required for this correction? It requires an redundancy, additional bits to be transmitted by the system. Okay. But however, with little extra transmission, forward error correction is possible. How exactly we do the forward error correction? You can see here, for every group of n chunks, it will create a redundant chunk by exclusive OR. You might have heard about the XOR. Okay, what is XOR? 1 0 is 1, 0 1 is 1, 0 0 is 0, 1 1 is 0. Okay, only when there is a different inputs, okay, then only the output is high, otherwise it is 0. So this is the formula being adopted in the forward error correction. It will create the redundant chunk by using the XOR operation with the n original chunks. So it will send n plus 1 chunk and increasing bandwidth 1 by n. Okay, it is a very small one. Okay, it can reconstruct the original n chunks if at most one last chunk from n plus 1 chunks. It means that if one chunk is lost or it is corrupt, then it could able to recreate it at the receiving point without asking for the retransmission. Hope you understood the forward error correction. It is one of the most appreciated techniques in the network system to either to overcome the loss or to overcome the error occurred in the transmission. The second possibility for forward error correction, you can see that it can be done by one more technique. As I told you, the redundancy is always required. But what we do here is a small resolution chunks are created for every chunk. You see here, this is the first chunk, isn't it? This first chunk will be developed a low resolution or which we can say a reduced bitrate chunk. Okay, a small chunk is developed and this chunk is added with the next chunk. Okay, and then it is transmitted here. So again, 2 has developed a small one. Okay, and that is added here. 3, it is added with the next chunk, that is 3, and 3 as I developed the small one and it is added with the next chunk, that is 4th, and then it is forwarded. So what is the redundancy? You can see that 1 is added, 2 is added, 3 is added. But what is their size? It is hardly 10 to 20% of the actual size of 1. Okay, so from these 3 you are added about 60% extra, not even one full chunk length. Okay, obviously this will help us in recovering the lost packet. You see here how it happens. Suppose assume that after transmitting this, the third chunk is totally lost. How can we regain it? Very simple. 1 is already there, 2 is there, third one is not received. It will be recovered from this and it will be recreated, whereas the fourth will be taken as it is. No doubt, third one will be having a low resolution, or what you say, the quality is degraded, but even a low quality of one chunk will not make a much problem at the receiving point because other 3 have the good quality. So this is how exactly the forward error check correction is making another technique to improvise the recovery at the receiving point. It's, I think, the beautiful technique that has been adopted here. Let us discuss one more technique. I think there are a lot of improvisations. Research has been done to improvise such error recovery, and this has come as the latest amongst them. You can see here in this technique, it is called recovery from packet loss. Here, the third technique, all these packets. This is actually the first one, second one, third one, and fourth one. Each of this chunk is broken down into smaller units, 1, 2, 3, 4. Here, second one is broken down into 5, 6, 7, 8. Third one is broken down into 9, 10, 11, 12. And the fourth one was broken down into 13, 14, 15, 16. Okay, so it means that whenever you do this smaller segments in it, when you forward this to the next level, what we do here, you can see this. The chunks are reordered and reframed. Rather, we say reframed. How? You see, only one segment of the first chunk is taken, and the first segment of the second chunk, first segment of the third chunk, and first segment of the fourth chunk. Altogether, it is formed a new chunk. Okay. Similarly, the second chunk, second segments of all these four chunks are added, and second frame is new frame is created. Okay. Third segments are added, and third chunk is created. Fourth segments are added, fourth chunk is created. Now, after transmission, assume that the third chunk has been lost. It can easily recover like this because now we know that the first chunk, original chunk, is the combination of segments like 1, 2, 3, 4. Okay, we have 1 here, 2 here, 3 was here, but it is lost. 4 here. So 1, 2, 4 are available. However, 3 is lost. A small portion of this is lost, and which will not really make a big difference. You can see in every other chunk, only one segment is lost, so that it will not make a big loss to the voice communication. Okay, a small segment loss can be understood by the receiver without any problem, and hence we say it is another way of overcoming the packet loss in the transmission. Okay, this is the beauty of these technologies that are used in the one. Well, I think now I am moving with the one illustration over the voice over internet protocol. As I was mentioned you earlier, Skype is the best example for that. It is an application which adopts the VoIP, voice over internet protocol, and there are certain application level preparations are made to make the communication effective. So let us see how exactly it will work, and it has been designed and it will work. Basically, the Skype was developed and it was used for a private communication, that is peer-to-peer communication. Okay, and this has been taken by the Microsoft in the year 2011. I think after that the Microsoft has got the proprietary, and because the Skype has got a lot of proprietary issues, a lot of technology depths are not available openly. But however, some vague analysis of Skype is very, very important and is possible. It has got two components. One is called a peer-to-peer component, where the clients are Skype peers connect directly to each other for voice over internet protocol call. You can see that these are the clients. They are connected each other through this super node. SN it is indicated. The super node it is another peer of the Skype which has got a special function. Okay, what is that function? It will give connectivity to all these clients or peers. Okay, so it is the local connectivity we can assume. Now you see that there will be overlay network established by connecting one super node with the another super node. Okay, another super node. Like this, a number of super nodes are interconnected. I think through this we can really make the communication from one client to the another client. Okay, and always the login is handled by the server, and there will be a Skype server which will take care of the authentication, because it is all the business application wherein the application service is possible only when you pay for it. Now let us look at the Skype client operation. You can see that The first joins a Skype network by contacting the super node. The client can join by making a request to the super node. So this client is added to this super node. And it will be using the IP address using the TCP. And it will do the login through the Skype server because it has been on a single authority to control the authentication, and then it will obtain the IP addresses for calling from super node to super node overlay. You can see this. It will try to collect all the IP addresses through this super node, and there is a super node overlay. Through that, it can collect all this information, and we say client buddy list is generated. Once it will do that, after that it can make the direct communication from this client to this client. But always it will go through the super nodes because the super nodes are the people who will give the connection from one client to the another client, or from one domain to the another domain. Here you can see that all these will be using the NATing. So obviously, when there is a NAT, we know one thing, that it is possible for us to see that whenever the NATing happens, the communication is possible only with the internal clients. It means that a communication from one node to another node, or one client to the another client within the network is possible, okay, by means of NATing. But this makes a limitation for communication from Alice to Bob. So now how they can do the communication? So for this, actually, they do a request to their super node. Okay, Alice make a request to the super node. Bob makes a request to the super node. They in turn will find out. Okay, and after that, you believe it or not, their communication starts with the support of the agent, and hence the communication completes. So this is how exactly the communication over the internet protocol is possible, and Skype is one of the most beautiful kind of an application that is being adopted for this purpose. I think it's a very beautiful application, and it will be using a very small bandwidth for the voice communication, and people are appreciated this and to a great extent, and hence it has become more popular also. With this, I think we can conclude the voice over internet protocol discussion. Any queries on this, please post to my email ID. I'm very happy to answer you. Thank you. Thank you very much. In the next class, we will be discussing on the protocols for real-time conversational applications like RTP and SIP.